you'll give me update as to do you want to continue. Okay, so...
Can you like do multiple points of entry?
Yeah, exactly. So what I'm going to do is I'm going to start off with the basics of what is cryptography. So there's lots of different definitions. The main thing is you want to transmit information in such a way that only the intended recipient can decode. And so there are a lot of different issues with cryptography. So a lot of it comes down to efficiency. It's not enough to be able to transmit information. You want to be able to transmit it quickly. You want it to be decoded quickly. There's also, of course, security. Anybody who has a target card, you realize right now that security is a huge issue. One of the earliest methods of cryptography goes back to the Greeks. They would take slaves. You could do a lot with slaves. You could shave their heads. You could write a message on their heads and let their hair grow back. And then the message is encrypted. Decryption is very easy. Shave the head. What is the problem with this method?
You need slaves.
One thing is you need slaves, and we are no longer allowed to do that anymore. Although grad students are close.
Anyone can shave them.
Anyone can shave them. So if somebody captures a slave, they can just shave the head. What else is a problem?
It's very unwieldy.
In what sense?
Well, you can't... First of all, I don't know what kind of code they would have been putting in people's heads.
Or you could write you could just write a message.
It takes a little while for the hair.
It takes a while for the hair to grow. So I almost think of having like a strategic reserve of of slaves, shave them all, put a bunch of messages, and then keep them in reserve. And then depending on the situation, I need slave number 348 because I need to send.
It's going to take a while, and if you still want that code, who knows if you still need it.
Right. So we need a better method than shaving slaves' heads and writing messages on it. So we want efficient ways to transmit messages. And so one of the earliest things that are being used is just the alphabet, and then just standard alphabet ciphers. So alphabet ciphers. So A, B, ... Z. And one way to do this is you look at all the different ways of rearranging the alphabet and write it underneath. So one of the earliest ones goes back to Julius Caesar, and what he did is he just wrote the alphabet shifted by 3 units. And of course, I'll use the standard English alphabet now. So A would go to D, B would go to E, Z would go to C. So if you wanted to send the message, cab, I guess I'll keep writing in black. Now, I don't know why Julius Caesar would want to send a message cab, but if you wanted to send the message cab, the letter C would now become the letter F, the letter A would become the letter D, and the letter B would become the letter E. And so if somebody receives the message FDE, if they know the Caesar cipher, if they know the code, they could figure out what the intended message was. It's very easy to decrypt. You just go backwards. Back when Julius Caesar was doing this, most people were illiterate. You almost didn't even need encryption back then. But what's wrong with this method of encryption?
It's too easy.
It's really easy. How hard is it to break this?
It takes a couple of tries, but you can figure it out.
How many tries?
Well, at least 20.
No, because you can also look for the frequency of letters and stuff.
So how many tries will it take you to decrypt any message using a Caesar cipher? Worst case scenario.
Are you saying it could be any number of shifts?
Any number of shifts.
And every letter is the same number of shifts.
Every letter is the same number of shifts.
Well, the number minus the alphabet minus 1, right?
Yes. We'll assume that they are clever enough not to have no shift. So we will assume that the message is encoded. So there's 25 possible shifts. And so, really, if you have a message like this, there's not that many possibilities. It's not that secure. Well, what if you do things that are more secure? And so, if people want, I've actually written a book for liberal arts students recently on how to use encryption and stuff like this. I'm happy to make some of the chapters available to you. There's more interesting things you can do. One of the things people did for a while is they did a Caesar shift, but they did a twist on it. I'll probably spell his name wrong. Binary, something like that. And what you did is you would take your message, the quick brown fox, and I need a short word from somebody, any word. That's not profane.
Dog.
I'm sorry?
Dog.
Dog. So what you do is you write dog, and you just keep writing dog. And now what we do is the D tells us how much to shift T by. So D is the fourth letter of the alphabet, so we would shift T by 4, T to U, V, W, X. So the first letter of the coded message would be X. H is shifted by O, I don't have to calculate what that is, but you would go through and you would shift everything like this.
Wait, say that again? How'd you get X?
D is 4, so I'm going to shift T by 4 letters. Shifting it to U is 1, to V is 2, T...
So you're incorporating 3 shifts into your...
Right. And so
Same.
every third letter is shifted the same.
So the H is the same and the E is the same?
No,
I mean, would it be X,
They've
H,
shifted
E?
the same.
I'm shifting T by 4 letters because D is the fourth letter of the alphabet.
So H would be shifted by 4?
No, because H is shifted by O.
Oh.
M is the 13th letter, N is the 14th, O is the 15th letter. So I would shift H by 15.
Okay.
G is the 7th letter, so I would shift E by 7. So E,
Okay.
F, G, H, I, J, K, L. I think this would go to L. And then O is, so M is 13, N is 14, O is 15. So I would shift 8 by 15. And that would give me my message. So when you're doing cryptography, it's very important that the sender and the receiver have a way of communicating and a way of agreeing what is the secret. So all they have to agree upon is to use the word dog. And as long as they agree to keep writing the word dog, they know the code. And now you can transmit messages. How many possible 3-letter words are there? Lots. So you have 26 cubed. So there's a lot more possibilities now. Okay.
Does it have to be 3, or that's just what he said?
Well, that's one of the problems is, if you want the message to be more secure, instead of using dog, what would you use?
Horse.
Horse. Elephant. Brontosaurus. Use bigger and bigger words. They don't even have to be real words. Take one of your favorite or least favorite Shakespearean sonnets and take the first letter of each line. People used to do this for their passwords. Because if you forget, what is it? John Donne, I think, Death Be Not Proud. If you forget what your password is, well, all you have to do is look up. I remember it's the first letter of each line of Death Be Not Proud, so I can then just go look up, oh, here's my password. And so in some sense you have a password encrypting a bigger password. And you just have to remember something small and you get a more powerful thing. So this is a really quick way for people to exchange information. And this is more secure than the Caesar cipher. Especially since the person who's attacking this doesn't necessarily know how long your code word is. It turns out that there's tricks people can do using advanced mathematics to figure out what the length is of your code word. And then once they know the length of your code word, how do you think they crack the message? So how would you try to decrypt a coded message where you have this kind of alphabet shifting?
You have 26 options for each letter.
Right.
You do that however many times.
Okay, but what if my code word is 20 letters long?
Well, some large numbers.
Well, if it's going to be beyond the scope of what your computer can do.
Right.
So let's say you know every 20th letter is encrypted the same way. So every 20th letter is some Caesar cipher. Let's go back a little bit, and how many different ways are there for me to shuffle the alphabet?
Just rearranging the
Yeah, just rearranging the letters.
26 factorial?
26 factorial. So I have 26 factorial alphabet permutations. I think that's around 10 to the 26. It's way beyond what you're going to be able to do in your computer. When I tell this to my students, I say, imagine your parents. For the most part, my students don't always have a high opinion of their parents' mathematical abilities. But a lot of times, their parents will solve alphabet ciphers that are in the newspapers. How are people able to solve the alphabet ciphers in the newspapers?
You look for the single letter words.
So one is you look for single letter words. So one thing you can do to make your message more secure is you remove all the spaces. And so if you remove all the spaces, that's going to make it a lot more secure. Then people can't look for, what's the A, what's the I. They can't look for what's the probably the THE. But what you can do is you can do a frequency analysis. You know, what's the most common letter in the English language? E. So if you have a sufficiently long text or enough, examples of text, you can start trying to figure out what the words are by guessing. I'm going to make the most common thing E. And then if I have a expression of 3 letters that occurs fairly frequently, and the third one is what I'm believing E is, I might guess that that's the word the. And it's amazing how powerful frequency analysis is. And so, frequency analysis, it's a little bit harder to do this here because it's broken up into all the first letters are shifted the same, all the second are the same, all the third are shifted the same. But you can still do a frequency analysis here, and you can still figure out, without too much trouble, what this is. Bless you. A couple of years ago, they actually discovered a message from the Civil War encrypted with one of these binary methods. And it was found in the bottom of a river outside Vicksburg. And so it was a message to the commanding general of the Confederate forces, and they were able to decode it. It's not hard on modern computers. And once you decode it, you understand why the message was never delivered. The message was basically just telling the Confederate general that unfortunately we have no more troops to give you to defend Vicksburg against Grant. You're on your own. And the message was supposed to be delivered on July 4th, the day that Vicksburg fell. And so there's really no point if you're the messenger to go into Vicksburg that's been captured and deliver a message. And so the message was just thrown in the river. And the South used certain key phrases frequently in their communications. And so just actually trying 1 or 2 of the most common frequently phrases was enough to figure out what the message was. They actually were using one of the standard ones. But there's a lot of other things you can do. This will give us some fun World War II stories. What I like is some of the best examples in cryptography use the least amount of mathematics. They use just being very clever, being very intelligent, exploiting people's mistakes. So in World War II, the Germans had what they believed was an unstoppable encryption method in Enigma. And they did not think Enigma could be broken. If the Germans had implemented Enigma correctly, that might have been true for the 1940s technology. But they made a couple of very key mistakes that allowed the Allies to crack it. And so it's a fascinating story. And again, if anybody wants, I have lots of information I can provide on stuff like this. One of the mistakes is there was a German station that always began the day by broadcasting the weather report. Well, if you know how a message begins, you can use that as a crib to start trying to figure out the rest of the message. So one of my friends is a number theorist, and he actually tried to just crack the message on his own just for fun. And just guessing that it began with some variant of the name of the commanding general, dear General Beauregard or whatever, was enough to figure out the encryption. And so when you're doing these things, you have to be careful not to do anything that's exploitable. And so if you start off with dear so-and-so, and you know who the message is sent to, that's a huge advantage. If you always start off by broadcasting the weather report, or sometimes people would broadcast the same bit of information twice just to make sure that things are being received on the other end without us. Oh, well, if I know you've just broadcast the same thing twice, that's a huge help. And so there's lots of small mistakes that are done that the Allied people in the ultra efforts to crack the Enigma were able to do and exploit. Probably my favorite story is the Japanese attack Pearl Harbor, December 7, 1941. Huge victory for the Japanese. But fortunately, what did they not destroy? This is a history question. What was not destroyed when the Japanese attacked Pearl Harbor? Lost a lot of battleships, lost a lot of planes. What did we not lose?
Radio towers?
Nope. In fact, we wanted to put our radar on a certain place, but it was not considered environmentally friendly. And so they had to put our radar installation in a less optimal place, which was not as good for finding the approaching of the Japanese forces. We didn't lose any of our aircraft carriers. All of the aircraft carriers were fortunately outdated. And so the conspiracy theorists are always, the aircraft carrier became the most important part in the Pacific theater. At the time, it wasn't always clear, people didn't really understand how important aircraft carriers were. There were some people who did, there were some people who didn't. It's always fascinating watching people's opinions change as the war unfolds. But we lost no aircraft carriers. So after Pearl Harbor, the US is on the defensive in the Pacific, the Japanese Empire is expanding, it's taking more and more places. And a couple months later in the spring, we find out that the Japanese are planning on attacking an island, or attacking a place called AF. And at the time, I believe the Japanese have 6 aircraft carriers and we have 4. And we're pretty sure AF means Midway, which is an island between Pearl Harbor and Japan. But AF might have meant Australia. AF might have meant Alaska. AF might have meant Hawaii. Might have meant Los Angeles or San Francisco. And so you're Admiral Nimitz, you're Admiral Halsey, you've got to decide what to do with the US forces. You believe the Japanese, you've cracked a lot of the Japanese code. But the Japanese have codes within codes, and they don't refer to the place by name, they refer to it by designation, by AF. Do you go all in and do you deploy your forces to catch the Japanese by surprise? But if you're wrong, Hawaii is exposed, the West Coast is exposed, Australia is exposed. What do? And so the solution the Allies came up with, I think it was Commander Rochefort, is one of the most brilliant ideas I have ever heard in my life. You have to find out, does AF mean Midway? So this is what the Americans did. On a very secure channel, they passed a message to Midway, and they told them to break their water pump. And then they told them, in a low priority message when you're just giving us your status, mention you have a broken water pump and you need a replacement or you'll be out of fresh water in 2 weeks. The Allies then later intercepted a Japanese message. And the Japanese message says, we've intercepted a message from AF. They have a broken water pump and they will be out of water in 2 weeks. And so it's a beautiful trick. And they got the Japanese to reveal that AF meant Midway. The US went all in. The Japanese lost 3 or 4 aircraft carriers, we lost 1, completely turned the tide of the war in the Pacific. One of the greatest examples of applied mathematics, figuring out what was being done. There's lots of different kinds of codes. You might have seen the movie Wind Talkers a couple of years ago. The one about the Navajo Indians being used in World War II. I think Kevin Costner. Okay, so the idea came back during World War I that very few people outside of the United States understand Indian dialects. And so there are some languages that are basically only spoken by that tribe. And so what if we use these people to do real-time cryptography? And they can just speak to each other in their language. Now, of course, Native American doesn't necessarily have words for aircraft carrier, tiger tank, B-52 ball, stuff like that. So you have to, create new words. I think tank came from the word turtle, stuff like that. A lot of planes came from birds. And then, you can create this whole language. And the advantage of this is you can speak in real time. And depending on the situation, you need codes to be secure for different amounts of time. And so the rules were you would never let a code talker be captured alive. They would be shot, because if one of them is captured, they can be tortured and they can reveal the code. But the ability to speak in real time and give real updates and not have to spend 5 or 10 minutes decoding things. Don't attack here. Attack 500 feet to the left. Concentrate your firepower there. It's a phenomenal tactical advantage to be able to do something like that. When you're looking at the planning of the invasion of Europe, D-Day, you needed codes that would be secure for a couple of months. And for the most part, when you're doing the planning, it's okay if it takes an hour or 2 to decrypt a message that's being sent. You just can't have the code compromised. Part of D-Day, Operation Fortitude, and then we'll get it back into some of the mathematics. So I think the European coast looks something like this. My drawing is not so good. France is roughly here, Spain is roughly here, England is roughly here. And so the D-Day, the question is, where is the invasion going to happen? And so I think Normandy is somewhere in through here, and Calais is somewhere over here. And the Germans were convinced that the Allies would attack in Calais, because it was the shortest distance, and you want your troops on the sea for as little as possible. And so the Allies took advantage of this. They created a fictional army around Patton. And if you've seen the movie Patton, a wonderful movie, Patton hits an enlisted man and gets into trouble. The Germans couldn't believe that Patton would be taken out of the battle. He's the Americans' best general. He's going to be out of the battle because he hit it. And it's not, surely something's going on. The Allies created a fictional army around Patton, pretending to be attacking the Germans here, using systems that they knew the British had cracked. And using systems that they knew the Germans had cracked. And so the Germans actually kept forces up in Calais. Hitler kept Tiger divisions, Panther divisions in strategic reserve. And when the actual landings happened in Normandy, Hitler felt it was a feint. And he would not authorize the release of the tanks. So much of cryptography, it's not just transmitting information, it's transmitting misinformation. And getting people to do what you want them to do, to confuse people about your true intentions. So, we can talk a lot about the mathematics of encryption, but if you're looking at applications, a huge amount of the applications is trying to confuse your opponent about your true intentions. As a Red Sox fan, the following name and salary is still painful to say. So a couple of years ago, the Sox greatly overpaid for Carl Crawford from Tampa Bay. Huge disappointment when he came to the Red Sox. The Yankees pretended to be interested in Crawford. They didn't want him, they wanted to drive up the price. And they succeeded beautifully. They got the Red Sox to up their offer to get Crawford, and prevent Crawford from going to the Yankees. And so much of cryptography and the science of encryption is controlling information, controlling impressions. What I want to do now is shift to a more mathematical topic, correcting errors. And so this leads to a lot of great mathematics, and in my mind, one of the most important inventions in the 20th century. So, detecting and correcting errors. So the idea is you want some system where if you make a mistake, the system can tell you a mistake has been made. What's better than telling you a mistake has been made? Knowing how to correct it for you. Right? That's great. Steve, you made a mistake. What you really meant is the following. Let me fix it for you. So one of the fathers of this, science is Hamming. And so Hamming, I believe he was at Bell Labs, and he was low man on the totem pole. So he only got to use the computers on the weekend. And these are the old punch cards. And what happened is, he would leave it in, and on the weekend they would run it in, and it would go about 15 lines, and there was an error. And he'd come in on Monday, and he'd be told what the error is, and the next weekend he gets to run it again, it does 17 lines, and he gets another error. And I will clean up the language, but the gist of it was, if it can recognize that a mistake has been made, why can't it fix the mistake? So what you wanted was a way to do information, so that the computer could detect an error had been made, and fix it. You see something like this almost every day.
Spell check.
Spell check is one example. What's another example? I consider it one of the greatest inventions of the 20th century.
Not GPS.
Not GPS.
When you're texting it.
Not texting. When you go to a store and you buy something, how do you buy something? The scanner. The barcode. The barcode, in my mind, is one of the greatest inventions, the barcode and the laser scanner. For two reasons. One, you get the product price correct. And two, the store gets to update its inventory in real time. You can even do better things for people who are teaching statistics. Did we talk about the target pregnancy story last time? Have you heard about the target pregnancy? So, a father in the Midwest, I think it was Minnesota, gets coupons from Target for pregnancy items. And is furious and is yelling at the manager, why are you giving me this? My wife and I are way past childbearing age. I've got a young son and a high school daughter. Why are you giving me pregnancy coupons? I'm very, very sorry. And so a couple of days later, the manager just follows up and just makes sure everything's okay. And the father's a little bit sheepish. And I guess there's been some activities with my daughter that I was not aware of, and I guess we do need those coupons. And so the question is, how did Target know? Well, when you buy things, you have your card, and if you scan your card, the stores give you a discount. They don't really care who you are. They just care which items are correlated. And so they can look at, they can recommend, and they want to get you to come back to the store. So they can do literally targeted marketing.
Well, that's like when you go to the supermarket and the coupons print out.
Yeah, and the coupons print
Oh.
out. How do they know? Well, because every time you scan in your card, they track all your purchases, and they know what things you like to buy. If you go to Amazon and you look at, if you watch something, on Amazon Prime, or you go to Netflix, and they look at, or you look at a product, people who bought this also like. They try to figure out good things to suggest to get you to buy. And again, for something like this, most people don't really care if they're using some of your personal information, if they can make your life easy and suggest, oh, that would be a good movie to watch. There was the Netflix $1 Million Challenge. And, they wanted somebody to come up with an algorithm that would do a 10% better job of predicting what movies somebody else would like to watch. And it was but somebody finally came up with enough things to push it, past that 10%. What Target does now is they print out those coupons that are relevant to you, but they'll also throw in a couple of coupons that are not relevant, so it looks like you just got a mishmash of coupons. You'll get the coupon for the diapers, and you'll also get a coupon for a new grill, a lawnmower, a tent. So it doesn't look like you're being deliberately targeted, but you will still have the coupons that they want you to have. So to me, the scanner is a wonderful invention. And it ties the applications of marketing, it ties great things in statistics and trying to figure out which things correlate well, which you try to get. And the scanner, it's not that hard to scan an item. So if you scan and it doesn't scan properly, what happens?
It doesn't beep or give you a little error.
Yeah, so what does the cashier do?
By hand.
I'm sorry? No. They scan it again. And if it doesn't work after 2 or 3 times, then they'll manually put it in. But it's so easy to scan it again that for something like this, you don't mind if you can't correct an error. You just want to detect an error. When you're scanning this, when I bought the M&Ms for today, if I'm charged a new car, I will notice this and I will be upset if I'm all of a sudden paying $20,000 plus for a bag of M&Ms. You give me the wrong product, I will be upset. But it's so easy for the cashier to just scan it again, and most of the time the scan works, fine, it's not a big deal. I don't need an algorithm that's so clever that it can correct. I just need an algorithm that can detect an error. The better one is an algorithm that can correct the error. So imagine you're downloading a big file from the internet, either legally or illegally. Some kind of movie. And all of a sudden, you start to play it, but there was an error in transmission. And so the entire file won't work now. And you have to download the entire large file again. This is not good. Right? You want to constantly be checking the data packets to make sure they're correct. Most of the time, most of the information transmitted should be correct. If most of the information is wrong, we're not going to be able to use these channels to communicate. So the probability of an error should be rare. But in a situation like this, there are 2 possibilities. You either detect an error has been made and then immediately retransmit those numbers, or even better, correct. So let's first talk about error detecting. And then as a mathematician, it's very hard for me to speak in English. I much prefer to speak in numbers. So I will only speak in zeros and ones for the rest of this. Because if I can transmit zeros and ones, I can transmit anything. So for instance, imagine blocks of 5 numbers. 1, 2, 3, 4, 5. And so all the numbers are either a 0 or a 1. So I have 2 possibilities for each of these. And 2 to the 5th is 32. So this is enough to give me all the letters of the alphabet and some punctuation marks. If I went a little bit further, if I did 2 to the 6th, that gives me 64 strings. I can represent all the letters of the alphabet, I can represent the numbers, I can represent all the punctuation marks. I could even have a special symbol for capitals and say the letter following this is capitalized. Or I could even add another string over here, and I could put the capital letters as well. Is it better to have a symbol that means the next letter is capitalized, or is it better to add another spot over here and now have 7 digits that I transmit? So which would you rather do?
Just one.
I'm sorry?
Just have the one that
Why?
indicates, well, it just consumes less. If you're talking about computing power, consumes less memory, takes less time to run. If you're doing this multiple times, that can add up.
There are fewer places for an error to occur.
I don't think it's So much fewer. It's related to the computation. How often do we capitalize letters?
Less frequently than not.
Less frequently, yeah. Most of the time the letters are not capitalized. So if I add another digit, everything I'm transmitting now has that extra digit that has to be padded on. Versus sending one extra block of 6 just when I need a capital letter. And so if you don't use capitals that often, it's much better to just have a special symbol that says next letter is capitalized than to make everything longer to transmit. And so a huge amount of the subject is how can I do things fast? So I'm going to just send strings of zeros and ones. So if I want to send a message, 0, and I want to send 0110. I want to send this message. And then the recipient, maybe the recipient gets 0111. Unfortunately, the recipient might not know, is this message received correctly or not? So I can't just send 0110. And so again, right now I'm going to assume I don't care about encrypting my information, I just want to transmit my information. So if I try to send this, the other person on the other end has no idea of knowing if they received the correct thing. I need to build some redundancy into my message. So does anybody have a method of transmitting information that would allow me to tell if an error has been made?
Transmit twice?
Transmit twice. So there's two ways to transmit twice. I could do 00111100, or I could do 01100110. In some sense, it doesn't really matter which one you do. You've got to do both. I slightly prefer this one because you can see as you're going along if you've made a mistake. And you don't have to wait till the end. So this is called Tell Me Twice. And Tell Me Twice is wonderful. It lets you know that an error has been made, and it lets you know where the error has been made, but it doesn't let you know what the error was. So if you now get 01111100, these two numbers are not the same. So you know there had to have been a mistake, but you don't know what the mistake was. Yes?
There's a similar application I come across with in statistics. We're talking about the probability of a non-detect or a false positive.
Right.
And it can be very, very small. But if you're doing a batch of 200, the probability that you're going to get one is actually pretty good.
Right.
And so the question in the class then becomes, well, how do you deal with that? The probability of every day, if you're doing this much data, you're going to get a non-detect. Right. Just run those non-detects or run those false positives again.
Right.
And see if you get the same thing again.
Did you talk about, is it better to do 2 batches of 100, batches of 50?
Well, the idea there actually is you don't need to do the whole batch again.
Right.
You just have to, the probability of getting one out of many is high. The probability of getting the same one wrong twice is very, very low.
Right. So. I mean, it's actually possible that you could have transmitted the message 11111100 and had 2 errors. But we will assume the probability of making 2 errors is very small.
Right.
If the probability of making 2 errors in quick succession is not small, this is a bad way to communicate. So Tell Me Twice is wonderful. It detects errors, but it doesn't correct them. Can you think of a modification that corrects errors? So this is one of Hamilton's great insights.
Well, if the probability of making consecutive errors is really small, you can do tell me 3 times.
Tell me 3 times.
Tell me thrice.
Tell me twice.
Right.
That's all we have to do now. Now we just tell me 3 times. And so if we do that, it's now 0001110 11111000. And so now imagine you receive 01011111000. You know there had to have been a mistake here. It's possible there was a mistake here, but you would have needed 3 mistakes.
So that's actually 0110.
I'm sorry?
So your first send is the 4-digit 0110, right?
Right, that's the message.
So that's the message. So
right.
if you say tell me 3 times, you string the first one three times in a row, the second one, rather than 0, 1, 1, 0, 0, 1, 1, 0.
You could do it either way, it doesn't really matter.
Okay.
To me, the advantage of this is I have all the elements next to each other that are supposed to be the same. If I did 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, I would have to check the first, fifth, and ninth.
Okay.
And to me, checking the first, fifth, and ninth is painful. Checking 3 in a row is much easier. It's just a way to process the information, but they're equivalent. So when you see this, what would you guess the message should be?
0, 0, 0.
It should be 0, 0, 0. It's possible the message was supposed to be 1, 1, 1, and you made 2 mistakes. But it's very unlikely that you had something like this. So the tell me thrice is a wonderful method of explaining something like this. So what I want to do now is I want to do a fun problem. So how many of you have ever seen hat riddles? There's a huge number of hat riddles in mathematics. This is one of my favorite versions. So you have 3 people, and we'll put them on an equilateral triangle. Each person can see the other 2 people, but they can't see each other. They can't see themselves. Okay? And I have 2 colored hats. And I guess based on the markers I have black hats, and I have red hats. And in this version of the problem, each person is equally likely to have either hat independent of the other people. Okay? Each person has hat added to head. Independent of others. Independent of others. And 2, 50% of the time it's red, 50% it's black. And we're going to play the following game. You can do the violent version, you can do the non-violent version. I'll do the non-violent version. Everybody closes their eyes, they agree upon a strategy, and then I say open your eyes, you have 5 seconds to look, and then based on what you see, you have 3 choices. You say red, black, or you stay silent. If everybody who speaks is correct, everybody gets $1 million. We'll just tell Henry that he has to up the financial support. If, however, even one person who speaks is wrong, everybody pays me $1 million.
What if nobody speaks?
If nobody speaks, nobody wins, nobody loses. So the question is, do you want to play this game? And if so, let's say we'll play this game many, many times.
You're guessing the color of your own hat?
You're guessing the color of your own hat.
Do
So,
both colors have to be in play?
I'm sorry. Sorry. So you can see the other people's hats. You can't see your own. And when you speak, if you are correct about your hat color, if one of your friends who speaks is wrong, it doesn't matter that you were correct. Somebody on your team is wrong. Everybody on the team owes me $1 million.
Are both colors in play, or could
Yes.
it be all red or all black?
Could be all red, could be all black. All possibilities are equally likely. I put the hats on independent of everybody else. So everybody has a 50-50 chance of having a red or black, independent of what everybody else gets.
Do you have a pool of hats that you're starting with?
Sorry?
Do you have a pool of hats that
Nope.
has unlimited number of
Unlimited
hats?
numbers.
So you have no idea what you could have on.
You have no idea what you could have on.
Why would you play?
Because you took this class.
Well, then why do you give the other people
Okay,
hats?
so give me a strategy where you will be indifferent to playing this game.
If I knew what the pool of hats
You
was.
don't know what the pool of hats are.
Well,
So give me a strategy where you're happy to play. You tell me what the 3 people say. There's a very safe strategy you can come up with.
you all just. Well, so you have to. You don't all just say the same word. You have, the 3 of us could say it completely, red, red, and black. We just all have to be right.
Yeah, if you say white, you're going to be wrong.
No, but I'm saying, when we all yell out at the same time, we
Yes.
don't all have to say the same color.
Correct.
But it's have to say
But everybody who speaks has to be correct. If 2 people are correct and 1 person is wrong,
Could we
you
have
lose.
hand signals?
Nope. You lost your hands. Monty Python.
Oh.
It's only a flush. Can you give me a strategy where you're indifferent to playing this game, where you won't lose any money?
If we all say no, or all stay silent.
If everybody stays silent, okay, so you're at least indifferent to playing this game. If I force you to play this game, fine. You'll play this game, you'll all be silent. I'll get frustrated, I'll kick the board, fine. Can you give me a strategy where you'll be right 50% of the time and wrong 50% of the time?
All say the same color?
Nope.
If you all speak.
Because if you all speak and you all say the same color, what are the odds that everybody is correct? 12.5 or 1/8. And then so 12.5% of the time you'll all be right, 87.5% of the time at least one of you will be wrong. So if you do that as your strategy, you will lose more often than you win. Can you give me a strategy where you win half the time and you lose half the time? So what's the strategy? You choose.
One person stays
Good.
silent.
Okay, one person stays silent. And
No, two people stay
Two
silent.
people stay
and
silent.
one person says whatever.
yes. Doesn't matter what they say. So person one will always say red. Since the hats are equally likely to be red or black, this person will be right half the time, this person will be wrong half the time.
But if the other two stay silent, then you don't win the money, though, right?
Nope. As long as everybody who speaks is correct, you win.
Oh, so two don't speak and
If
one
two don't speak
speaks.
and one speaks, you're fine.
You don't win, or you don't.
You don't. As long as nobody's incorrect, you're okay. So if even one person is wrong, the team loses.
So if the two stay silent, the one's wrong,
Then you lose.
then you lose.
If two stay silent and one is correct, you win.
Do you win or do you not get?
You win.
Oh, you do.
Yep. As long as everybody who speaks is correct,
Oh, who
you win.
speaks?
Who speaks? It's very important. It's only the people who speak that matter.
So can those three people strategize before the game starts?
Absolutely. They can take math. Lots of math. So they can take as many math classes as they want.
But I mean, can they talk to each other?
Before you
Before
take
the
class,
game
yes. Yes. So,
Still not worth it.
well, the strategy we have only works 50% of the time.
And if you don't win, you lose.
And if you don't win, you lose. So you lose 50% of the time. So this strategy will make you indifferent to playing. Half the time you win, half the time you lose. Your expected payoff is 0. Is there a way to do better than 50%? It doesn't seem like you should be able to do better than 50%, because I'm just putting on the hats randomly. There probably is a way to do better than 50%, because I'm talking about this problem now. You can actually do better than 50%. You can come up with a strategy where you win 75% of the time.
Is there any winking
Okay.
involved?
Nope. you lost your eyes before. You can't lose your eyes because you need to be able to see. Yes?
Two people say the same color?
Which two people?
It doesn't matter if it's the same
Any
color.
two, and the
people
last
don't
person
like
stays silent.
Well, if two people say the same color, the probability they both have that color is 25%.
Yeah.
So you would lose 75% of the time.
And you all have to speak at the same time.
You have to speak or stay silent. All that matters is everybody who speaks has to be right. If you're silent, that's okay.
But it has to be at the same
It
time.
has to be at the
It
same
can't be like
time.
in succession.
Doesn't matter, because if you find out what the first person,
It doesn't.
But
Yeah,
if the first
I'll
person's
do it.
right,
Because I know you're more likely to have two the same.
Okay, so Linda's on the right track. How often do you have two hats that are the same?
Half.
Well, let's look at all the possibilities.
Well,
So,
yeah.
So the hats could be
black, black, black.
Well, it's
black, black,
Yes,
black,
yeah.
black, black,
Yeah.
Red.
red. Let's use the red marker.
Red.
6.
Red,
And red, red.
red,
Red, black, black. Red, red, black.
black, black, black. And now I could have Red.
black.
red, black, black, black.
Yeah, 1, 2, 3, 4.
So if you look at this,
Yeah.
in these 6 over here,
That's
2 people have the same color hat and 1 person has a different color hat.
So if you see the other two people with 2 different colors, you're gonna assume
That you have the same as one of them.
that's still one.
That stays
That's
silent.
still where you were.
So only if you see that they both
Say
have the same color.
If they both have the same color, then you say you have the opposite. So if 2 people have black, you say red. Because the majority of the time, it's 2 to 1.
But you still have a 50, it's like flipping a coin though.
But it's not 50-50 anymore. Because if you look at the 8 different options, options, 6 of them, 2 are the same color, 1's different. So you
Odd
have
is
6,
really
3/4 of the time, you're going to have the other color.
So
If
in,
they have the same color.
so in these 6 cases, only one person speaks.
This is simple probability. This I get.
Only
The other
one person speaks in these 6 cases. We don't know ahead of time who speaks, but we know that there's only one person who speaks. What happens in these cases, the 2 other
But you
cases?
don't. But that's so when you at the beginning when you're deciding your strategy. If you all have the same, so okay, can I talk this through?
Absolutely,
So
go
if
for
you
it.
all have the same color,
Yes.
like, well, if you look out and you see 2 blacks,
Right.
you're probably going to say red.
Mhm.
But 2 out of the 8 times, or 4 of the time, you're going to be wrong. So how do you decide who speaks out? Because at that point, everybody's going to
Here's
speak.
the rule. If you
right?
ever see 2 hats of the same color, say the opposite color. That's your rule. So imagine you're in this case.
So that would be everybody would.
Everybody would speak. Everybody would
So
say
you
red.
get it wrong in that chance.
Everybody's wrong.
Okay.
Now in this case, only the 3rd person speaks. Because the 2nd person sees a
Right.
black and a red.
So
The
it's
1st person sees a black and a red.
So 7%.
So here, in these cases, only one person speaks.
Right.
In these 2 cases, everybody speaks.
And you're wrong. In
And
those
they're
2
wrong.
cases, you would be wrong.
Not only
In all
are they
the other
wrong,
cases,
but they are
right.
damn wrong.
25%. So
Okay,
there's-
this is you gotta put in some real good adjectives here. This problem is fascinating, and it's actually related to what we just did a few moments ago with cryptography. It's related to the tell me 3 times. 0, 0, 0, 1, 1, 1. If you see 2 things that are the same and one is different, and you want to correct, how do you correct? I correct all 3 being the same. This is related to the cryptography, it's related to high dimensional generalizations. This is the 000 code word, this is the 111 code word. This is the tell me 3 times. This is a very fun way of explaining the mathematics behind it. Is these 2 words are very well separated. So if I look at all strings of 3 letters, I have 8 possibilities because it's all 0s and 1s. And so I have 0, 0,
So this is binary.
This is binary.
Binary.
This is binary.
Can I go back for 1 second?
Sure.
I'm having one of those moments where, like,
A good moment or a bad moment?
the Monty Hall problem where you're like, yeah, I totally get it. And then
Okay.
5 seconds later, you're like, no, I don't. What?
Okay.
What? So, just to go back for 1
Sure.
second, with, if you are seeing one of each color, I can see where
If you
you're
see
running.
one of each color,
You say
Right.
that.
then you say nothing. You only speak if you see 2 hats of the
Oh,
same
sorry,
color.
then I do get it. Thank you.
Okay.
So you're going to lose
Okay.
a quarter of the
You
time.
lose a quarter of the time.
But
So-
you'll win 3/4.
So here's the thing. You don't know what hat color you have. Can you do better than 50% in terms of getting your hat color right?
Okay.
So
your
this goes back to the birthday problem we had at the very beginning of the day, with the slight differences between 2 questions and how important it is to phrase things properly. Can you ever do better than 50% correct for your hat color? No, because I put down your hat independent of everybody else. It doesn't matter what you see. Your hat is as likely to be red as it is to be blue. Let's think about what goes on. Let's look at the 3rd person. The 3rd person speaks and is correct. So we're going to just make a chart for the 3rd person. In the first case, the 3rd person is wrong.
But everybody would be wrong.
Everybody would be wrong. In this case, the 3rd person is correct. In the next case, the 3rd person is silent, 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 silent,
Wrong.
wrong.
So you're wrong more than you're right.
Wait a minute, there's one. No, sorry. In this case, the 3rd person speaks and is correct.
Oh.
Right. So it was right. Okay, so it was wrong, right. Then it was silent, silent, right, silent, silent, wrong. So if you look at the 3rd person is right half the time the 3rd person speaks.
And the same would be true for the other.
So if you look at the second person is wrong, silent, right, silent,
Again, the rule is silent if you see
Right.
2 different.
Silent wrong.
if you see
Same.
2 different.
2 different.
Right. So
Can you explain why it's silent on the first one then? With BB?
No, the first one is wrong on the first one.
Okay.
The second person is
They would've
wrong.
said red.
But the second person,
They would've been wrong.
the second person is silent here. The second person speaks here is silent.
Okay.
Is silent. Then the second person is correct, silent, and wrong. The first person is wrong, and then it's silent, silent, right. And then
Silent right.
silent, silent, right, silent, silent, right, silent. Alright, so it's kind of tough to tell the way I've drawn things here. But
I did it as a tree diagram and it sort of breaks out.
this goes to here.
Fairly,
But if you notice what's happening, in each row, how many checks do I have?
One.
Or
so that's
0.
your 6 out of 8.
That's my 6 out of 8. So I never have two people speaking that are correct. Each person is right only 50% of the time. But what's great about this is the way you arrange how right they are. Everybody's right twice. Everybody's wrong twice. But when you're wrong, boy, are you wrong. Everybody is getting it wrong.
That's helpful to look at its totality. So when you teach it, do kids have the problem that I have? They don't have this problem. Where if you think you're just guessing one color, when you're looking at it just by yourself, through the lens of one person,
Right.
as opposed to looking at it in totality, you think it's only one out of.
I mean,
Right.
when you look at this, when you first see this problem, you should not be able to do better than 50%. Seeing the other hats doesn't help me figure out what hat color I have.
As an individual, you can't do better than 50%.
As an individual, you can't do better than 50%. But as a team,
But the good thing is, if anybody's wrong, nobody can blame you because everybody's getting it.
exactly.
It's similar to the Monty Hall problem in that you have to focus on the number of possible outcomes
Right,
and look
right.
at it as a
Right.
fraction of possible outcomes, not the probability of each individual decision.
Right.
It all comes down to the metric. Do you think being wrong with all three people speaking incorrectly is as bad as just one person's wrong? So here we're saying it doesn't matter how wrong you are. If you get the wrong answer, you get the wrong answer.
So like the prizes behind us. Maybe that's not Unpause. That's what
No, I know. I was
Yeah.
thinking of those
Yeah.
movies. Oh, Monty Python. I'm like, I don't know what you're talking about. Monty
Monty
Hall.
Hall.
Okay. I know. That's like, let's make a deal.
Right.
Yeah,
Right, you have
yeah,
three doors.
Right. Yeah. Okay.
Carly
I have seen that.
Right, and for that you've got to remember, if the prize is behind a certain door and you haven't chosen the door, the host won't open that door. And so the host can't open a certain door because it would reveal the prize. Alright, let's see. Let's open up one of the doors you haven't opened up. Oh, it's the brand new car! So do you want to keep the sheep behind your door, or do you want to change to the other door which has the other sheep? Well, at this point it's now gone. So this is why you always want to switch in the Monty Hall game. Because if the prize is still in play, the host can't open that door.
So
So
if
here,
everybody knows about that, how's that show still on television? That's what I don't understand.
is it still on television?
Yeah, because it's what's his name does it?
And everybody doesn't know, and a lot of people don't believe it.
Right.
It's hard to get your mind around why you should switch.
That doesn't mean as an individual you're going to win. It just means if you played it many, many times, you'd have a better chance to win.
Yeah, it's still only a 2/3 chance
Right.
of winning.
But going back here, it all comes down to what metric you use to evaluate things. I mean, this is one of the big themes when you do statistics. How do you measure errors? So if you teach statistics, you might teach you the method of least squares versus using absolute values.
Yeah.
Why do we use squares? Well, if we use squares, the tools of calculus are available. We can have beautiful closed form expressions for best fit parameters for linear fits and recursions and recurrences. Regressions. But to me it's a little bit more unnatural. Why should you square the error? This is saying one error of 2 is worse than 2 errors of 1. One bad data point that has a pronounced effect, and one, you sneeze while you're recording the data, that will have a huge impact on the best fit line. So in some sense, using absolute values in statistics is much better, but the tools of calculus are not available because the absolute value function is not differentiable. Over here, we are saying that all that matters is everybody correct or is everybody incorrect? You're trying to figure out how to transmit things. And so this is very similar to the tell me 3 times. And so the idea is, if you want to draw what's going on, and you draw a nice picture, what's going on here is you have 0, 0, 0, And then you have 0, 0, 1, 0, 1, 0, 1, 0, 0. There's lots of different ways of doing it. 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. And now things get a little bit messy. So this differs from this in one place. This differs from this in one place. This differs from this in 2 places, I think. No, 3 places. So you then have all the different ways of encoding things here. So these differ in 3 places. It's not possible to differ in just 2 places. Right? I have 3 digits. If 2 digits are... Oh, no, I'm sorry. You can differ 2 digits.
2 digits could be switched.
2 digits can be switched. Okay, so now 0, 1, 1, 1, 0, 0. These would also differ in 3 places. So I could connect that with the green line. 0, 0, 1, 1, 1, 0. These would also differ in 3 places. And now this one and this one, they differ in 2 places. And so I could use all these different colors to try to keep track of how far apart things are. 1, 0, 0, 1, 0, 1. These differ in 1 place. So this would be, I think, a red connecting them. This would be a red. Oh, wait, this, I guess, they only differ in 1 place. So you can fill in the table and just see how
like
far.
Mastermind.
I'm sorry?
It's like Mastermind.
Yeah. Yeah, if you played Mastermind in terms of what information you have. And so the idea here is you have 2 special words. The 111 word and the 000 word. And you have a space of here 2 cubed or 8 words. And what we're doing is we're going to measure how far apart 2 words are by the number of digits that differ. So these words are all 1 unit away from here. This word, its neighbors that are 1 unit apart are these 3 words. So what we're really doing is we're splitting our space in half. And all the stuff in the top is within 1 unit of 000. All the stuff in the bottom is within 1 unit of 111. What really happens is when you try to do this in higher dimensions, this comes down to sphere packing. And so there's a lot of beautiful mathematics. I don't want to get too technical.
You mean like stacking oranges?
In some sense, yes. Except these oranges might be in 2,000 dimensional space. And so they're very strange oranges. But what goes on here is I'm splitting my space into 2 special code words. And then all of the other words in my space are within 1 unit of these code words. So I agree ahead of time that I will only transmit 000 or 111. That's going to be the only thing I will say. If you see anything else, it must be an error. So if you see one of these things now, you know there was a mistransmission. Well, what's nice is if the probability of an error is small, then if you saw one of these 3, almost surely this is what was meant. If you saw one of these 3, almost surely this was meant. And so this allows you to correct an error. And so this is the basis of Hamming codes. So this allows you to have 3-digit messages that transmit information, and you can correct an error. So the question is, how good is this method? How much of your transmission is information, and how much of it is redundancy? So what fraction of your message is actually information? A third. So only a third of your message is information. Essentially, this is the tell me 3 times. 1 out of every 3 digits is information, 2 digits are redundancy. There are generalizations of Hamming codes. If you go to Wikipedia, Wikipedia has some beautiful articles on Hamming codes. And just how you can push this problem a little bit further, or if not, I'm happy to just give you a chapter I wrote for the liberal arts book on how to use Hamming codes. And so there's a Hamming code, it's called the 7-4 code. You transmit blocks of 7, and 4 of the digits convey information, 3 of the digits are check digits. So the reason the Hamming 7-4 code is so important is 50% plus is actually information. So to me that's a psychological barrier. I want to be able to say at least half of my message is information. Being at the point where only a third of the message is actually the content you want to deliver is annoying. And then there are generalizations of this which allow you to correct and fix 2 errors, or 3 errors, or 4 errors. The problem is, the more errors you want to correct, the bigger the code has to be and the less information you can transmit. So when errors are very rare, you want to use something like this. When errors become more and more frequent, then you want to use something that's capable of detecting and correcting more errors. Any questions so far about detecting and correcting codes? So just kind of finish off a unit along this. I wanted to talk a little bit about UPC symbols. Do people know how these symbols work and how the scanners work?
I took a class and we talked a little bit about it, but I don't really remember it. But it was interesting.
So there's lots of different ways you can do UPC code. I'm going to just do the most basic. There's more involved ones. So UPC. Or barcode. So imagine you have a string of numbers, 1, 4, 5, 6, 3, 8, 2. And you want to make sure that this number is correctly read. So the following system is frequently used. I probably shouldn't have chosen such big numbers, but let's add up these numbers. 10, 19, 20, 29. Okay? So if I add up the numbers, I get 29. So I'm going to add a digit to my message. What digit do you think I should add? 1 is possible. 0. Why 1?
Make it even 3? No? Is that not what you're thinking?
Nope, that's perfectly good.
Okay.
So you can either add a 1 or a 9. Either one is fine. So you add, you can either write, you either write down what you need to make it come up to adding, with a 0 at the end, or you just write down what's the remainder when I divide by 10. So we can write a 1. Or, and so now we always pad our messages with 1 digit. And so now when the computer reads it, if the sum of the numbers is not a multiple of 10, it knows it made a mistake somewhere. So if it reads, 1, 3, 5, 6, 3, 8, 2, 1, it knows there's a mistake. And then the scanner has to go again and get the...
Well, what if you put a 2 on the end? Would it know
So
that?
if you got...
No, like you keep the original 1, 4, 5, 6, 3, 8, 2, 2. Would it know?
Yeah, no.
So I got this.
Non-10.
Yeah.
So now I get 31.
Right.
So it knows that a mistake was made.
Okay.
It
It
doesn't
doesn't
know
know
where.
where.
It has to be divisible in 10?
Well, I'm saying your message is this. So when you're writing your barcode, you always choose your final digit to be such that the sum is a multiple of 10.
But the problem could be with your padding
It
digit.
could be with your padding digit,
Or it
which
could
would be
with-
really annoying. You actually read the message that counted correctly. You just read the check digit wrong.
Right.
And so this is definitely an annoyance. But this is the basis of how scanners work. Is you want to make sure the computer has correctly read this number, and for the most part we'll assume that the probability of lots of errors is small. Now there are other things you could do. You could flip the 1 and the 4. And so there are more involved methods people have rather than just adding a 1. Now I don't really want to go into the more involved mathematics. If you want to look it up, the Wikipedia article is pretty nice. I'm happy to share chapters from my book. And it will explain how you can have a more involved configuration. One of the ones that people often use is you take all the odd numbers and you multiply them by 1. You take all the even digit numbers and multiply by 3 and add that number together. And that's the basis of your code. And by multiplying some of the numbers by 1 and some of the numbers by 3, it actually helps you if you transpose 2 numbers and write 8, 3 rather than 3, 8. It catches stuff like that. I mean, if you're typing, this is a mistake you make all the time when you're typing. You know, one of the fingers hits just a little bit earlier than the other, and you've transposed the order of two numbers typing from your left and your right hand. So having a method that can detect transpositions is very advantageous. There's a lot of similarities with something like this. Another nice example is, let's say I have a message of 4 digits. And so I have x1, x2, x3, and x4. I have 4 numbers. They're all either 0 or 1. And what I'm going to do is I'm going to add some check digits. So I'll add check digit 1, check digit 2, check digit 3, check digit 4. And what I'm going to do is, if these numbers are both even, my check digit will be 0. If they're both odd, my check digit will be 1. So for example, if I give you the message 1011, even plus odd is odd, so my check digit should be a 1. 1 plus 1 is even, should be 0. 1 plus 1,
0.
0. And then 0 plus 1. So that would be the 8 digits I would transmit. I would transmit 1011, 1001. How much of my message is information?
Half.
Half. So somebody choose a number, choose either an X or a C.
X.
Which X?
1.
Okay. So let's say we transmit X1 incorrectly. So now everything else is fine, but now we accidentally transmit this. Okay? You can tell from these where your error is.
Yeah.
So look, 1 plus 1 is 0. Good, this row is correct. 0 plus 1 is 1. That column is correct. 0 plus 0 is 1. There is a mistake somewhere in this row.
But it can't be on the right because the bottom's fine.
I'm sorry?
It can't be the right because the bottom's fine.
Which right?
No,
This?
the right in the box. Yeah.
The right column.
That one.
Well, that's right. It can't be here because we know this column is correct.
Okay.
We know there's a mistake in this one.
Same thing.
So it
And
has
the
to be
one's
the,
just like
has to be the
It has to be upper left. So this method not only detects an error, but corrects it. So the Hamming 7.4 code does better than this. You know, it has a majority of the message. This only has 50% of the message's information. But you know, again, that's a psychological barrier. You know, half of what you're transmitting is information. There's no need to put something down here that's redundant check digits. But what you have here is it points out exactly where the error is. And you can go through all the other possibilities. You can go through, well, what if this check digit was wrong? Well, if this check digit is wrong, this is right, this is right, this is right. The only error is down here, these two are right, error has to be there. So stuff like this is extremely important in your streaming video and stuff like that. You want to be able to transmit the information quickly. You don't want to have to download the whole thing again. And so I've been uploading the first video onto YouTube. And so it takes a long time for YouTube to upload things. Okay, it has successfully uploaded, but it takes about an hour to upload a lot of these videos. So my question is, how would you generalize this? What could you look at next? So again, when you're teaching, I know it's tough to find the time, but especially if you have talented students, whenever they have a unit, ask them, what would you do next? How would you generalize this method? What could you look at next?
Could we expand the size?
Sure. So what would you like to do?
3 by 3.
3 by 3.
6 check digits.
Okay. Cool. Alright, so you've got a 3 by 3 now.
Could you do a 3 by 2? Does it matter?
You could do a 3 by 2, and then the question just becomes, what's the most efficient way? What's the best way? Let's look at a 3 by 3 now.
How much information you need to
How
send.
much information are you getting? How much check digits are you getting? So now we have something like this. So, we'll put in actual numbers, 0, 1, 1, 1, 0, 0, 0, 1, 1. this would be 0, this would be 0, this would be 1, this would be 0, this would be 1, this would be 0. It's like tic-tac-toe. Somebody give me a square to change. Middle. So we incorrectly record a 1 over here. And now we play the exact same game as before. In the first row, everything is fine. It passes the check digit test. The second digit, it fails. So we know there's a mistake somewhere in this row. The third row, it passes. The first column, it passes. The second column, it fails. There's a mistake somewhere in here. And in the last one, it passes. So it's uniquely specified where the mistake is. The mistake's the middle square.
What if there's 2 mistakes?
If there's 2 mistakes, this is being recorded, so I can't use the correct phrase, but you know.
Okay.
So this will not detect 2 mistakes. This will detect 1 mistake. How much of my message is now information? So I think 9 out of 9 plus 6. So that's 9/15. So if I divide by 3, it's 3/5. 60%. 60% of my message is now information. And I'm still able to correct 1 mistake. We've broken the 50% barrier. It's not quite as impressive as breaking the sound barrier, but we've broken 50%. And again, this is just elementary algebra. If you want to do a unit, if you want to try to motivate people on applications of algebra, everybody's watching clips on YouTube, everybody's watching streaming video on ESPN or something. How do you download this stuff? How do you make sure the packets are being correctly received? If you spend too much of your message on data integrity checks, you're going to get bored. It's much better than when the streaming video first started. I remember how long it would take to watch things. Now, even if the internet connection is even weak to moderate, I can watch streaming video without any trouble. We've broken 50%. How could we do better than 50%? How could we do better than 60%?
Just make it bigger.
Make it bigger. So in the limit, what fraction of our message is information?
100%.
100%. So why don't we just keep making it bigger?
More errors.
More errors, right? So eventually, if it becomes so big, we start having 2 errors, or 3 errors, or 4 errors.
You can't detect that.
Well, then it becomes interesting as to what would happen if we had 2 errors.
How do you, sorry, different question, how do you optimize?
So,
So
that's a great question. It becomes then a question of how often are you making errors?
Right.
The more frequent errors are, the smaller size you want to eliminate the possibility of 2 errors.
Well, isn't this like manufacturing? Like you have the computers do all of it and then human check the final stage?
Well, you want the computers checking things. You don't want the human to have to check things.
But don't you assume that mechanical things can make errors?
Absolutely.
I guess humans can too.
Humans can make errors. You're having so many bits of information being transmitted, it would be impossible for the humans to have enough time to check.
But you know what I'm saying? Like, you know how clothes have stickers in them? It's like checked by number 2.
Right.
I don't
Added
know
by
if
a
they still
computer.
have those. I haven't seen them lately. But computer number 2.
Right.
Gotcha.
Or just maybe the human is overlooking computer number 2. Any Futurama fans? Bender and Hermes? Hermes was actually the one who checked Bender when he was in the factory. It was a very nice, touching episode. Let's say we had 2 errors here. Let's see what happens. We'll put the 2 errors in different columns. So over here, this would now be wrong. Wait a minute.
If you make the middle
Oh, wait a minute.
block.
I erased 1 and I put 1 in its place. So let's say we now have this. So now we know that there's a mistake here, right? And now this column also would have a mistake.
Looks like there's
So you have 4 errors.
So you have 4 possibilities. And so the question is, these 2 could be wrong. And if I flip those 2, I'm okay. If I flip these 2, if I flip this wrong, then that's okay. If I flip this to a 0, this is now okay. If I flip this to a 0, This is now okay, and this is okay. So these two could be flipped, or those two could be flipped. So unfortunately, if there are two mistakes, I can't detect what the correction is. And so in general, if you have an n by n square, you then have another n check digits here, and another n check digits here. And so your information is n squared over n squared plus 2n. And so our formula here is just the special case when n equals 3. Can you think of any other possibilities? So we tried, bigger and bigger squares. What else could you do? I'm not saying whether or not it's better, but I'm saying, what else could you try? How else could you try to generalize this?
Different things. Is that like binary?
So one thing is to use something other than binary. Our computers love binary, and so to keep them happy, we'll stay in binary.
A non-square.
Okay, so one thing is to try another shape. Could you try a triangle? Could you try a hexagon? The square is very nice in terms of how things go. And so, but one thing is, could you make a triangle work? How would you do things there? Because now, here everything has the same number. Every row, every column has 2. With a triangle, maybe I'm losing that. But maybe I try a hexagon, or maybe I try a triangle, and I try another triangle around, I don't know. One possibility is to try other geometries. But what else could I do?
3 dimensions.
3 dimensions. Yeah, it is make like a Borg cube. And now you would have a plane of check digits here, a plane of check digits here, and a plane of check digits here. And then the question becomes, is it better to use cubes, or is it better to use bigger squares? Are some better in some ranges and others better in other ranges? I will deliberately not comment more. And you'll leave it as something to think about, something to give a student. What's the best way to handle something like this? And so one of the hardest things is thinking of new questions to ask. And so what's really nice about a lot of these problems is there's so many open-ended things you can do. So, in something like this, we could push it to higher dimensions. We could push it to 4 dimensions or 5 dimensions. So I'm teaching multivariable calculus right now, and, I'm talking to my students, for the most part, we only care about 2 or 3 dimensions in this class. If you want to study the orbits of planets, if you want to study, your professor's wandering while he's lecturing, hell, for your professor wandering, that's probably just 2 dimensions, Unlike some of my colleagues, I don't jump up and down too often in the lecture. But formally, when you do calculus, when you do vector analysis, you can have 5, 6, 7, 8 components. I just can't visualize them anymore. But formally, you can still work through it, and you can still set this up with a 4-dimensional hypercube. I can no longer visualize it, but mathematically I can still work with it, and I can still define where my check digits are. So again, in terms of trying to find units that can be brought in, this has a lot of advantages. You can talk about base arithmetic. Why do we care about different bases? I remember, I think it was in high school when we talked about doing bases other than 10. It seemed very strange as to I have 10 fingers. Why would we do things in bases other than 10? And a lot of it comes down to how efficiently can you compactify information. And this is why I wanted to do that problem at the very beginning about how do you divide up a number like 100. And the best way to divide it up, so that the product is as large as possible, that's really related to how much information you can convey with a given amount of knobs and dials.
Sorry, a little bit off topic.
Yeah.
What's the history? Isn't computing memory base 8?
Is that hexadecimal?
Hexadecimal is base 16.
I thought something was base 8.
There are some things that are base 8, there are some things that are base 16. So there's a lot of things that are hexadecimal, which is base 16, and after 9, you have A, B, C, D, E, F, and then 0. So 10 is 16.
Right.
And A is 15. I'm sorry, A is 10, B is 11, C is 12.
Values for
But all of these bases, base 8, base 16, they're really base 2 on drugs. Right, they're just a bunch of base 2s together. Base 8 is really just blocks of 3 now. And so it's just a question of what's the most efficient way to process things and store things. You want to be able to view the code. And so if you do things in base 2, the code starts to become very long to look at. But if you're using hexadecimal, you're going up to 16 now isn't so bad, and you just use a couple of letters.
It just gives you the ability to compress.
Yeah.
Okay. So it's efficiency.
So a lot of it's just displaying information as to how long would it take to actually write something down. And if you're writing things down in base 2, things go a bit further. One of my favorite, the Futurama is a wonderful TV series. It's by the creator of The Simpsons. A lot of the people who work on it have a lot of math and science backgrounds. And so there's one episode where the robot inherits a house from his uncle. It turns out to be a haunted house. And they see a bunch of numbers in 0 and 1 written in blood. And they ask the robot, what does this mean? He goes, I don't know. And then later in the episode, the robot sees the number in a mirror and starts running away screaming. And so what the writers did is they took 666, the number of the beast, and they wrote it in binary backwards. This is, very few TV shows would go to such great lengths, for a math joke.
You know all the squiggles, the alien language, is
Yes.
code, if you followed it from the beginning of the series?
I've heard that. Do you know what it's saying?
I have no idea.
I mean, they love putting in stuff in these episodes. The Simpsons has a lot of good math hidden in as well, a lot of their stuff. A lot of good Harvard Yale jokes as well, which makes sense where we are. But you're going back to what computers use. Really, hexadecimal, octadecimal, and whatnot, they're all very similar. Here's a really bad joke. Why does the computer scientist confuse Christmas and Halloween? In base 8, 31 is 3 times 8 plus 1, which is 25. So October 31st, Oct 31 is dec 25, decimal 25.
I do teach some of my 6th graders number bases, so I start with saying 13 eggs is a dozen. How is it sum?
Baker's dozen?
No, it's, base would then have to be for it to be 12, right? 13 eggs makes a dozen.
So it would be base 9?
Base 9, right.
Okay.
So it's just an inch.
Right.
So and it is fascinating for young minds to realize that the number system is fairly arbitrary.
Yes.
And so they get into it.
Right. I mean, I can't prove that the universe doesn't care how many fingers we have, but I don't think the universe cares how many fingers we have. We happen to have 10 fingers. Is there some fundamental reason for 8, 10, however you want to phrase it? What really matters? And so for problems like this, it's very easy for computers in terms of on, off, in terms of signals, to use base 2. As long as we're talking about base 2, I need a volunteer who's either willing to share their birthday with the class or make up a day during the year.
March 3rd.
Okay.
Oh,
Let
I
me-
was going to say.
Have you seen my cousin Vinny? And only Mrs.
I'll use somebody else's birthday.
Alright,
And I think my brother's.
okay. So I will guess your brother's birthday in 10 questions or less. And if I'm wrong, you have to say earlier or later. Does anybody know how to guess someone's birthday in 10 questions or less?
Break it into halves.
I'm sorry, break it into halves. Binary search. So, was your brother born on June 31st?
Later.
Okay. So now I know it's somewhere between June 31 and the end of the year. Alright, so June, July,
There's no
August.
June 31st though.
June 30th.
It's just easy to try to have to worry about things. Alright. So June, July, August. I'm sorry, July, August, September. So we'll go November 1.
Earlier.
So now I know it's somewhere between here. Every time you just keep splitting in half.
Why would you go to November? That's not halfway.
It's halfway between here and December 31st.
It's 2 months. Is it?
Well, this is really this is July 1st.
November.
Oh,
November,
that's 2
December.
months, and that's 4 months.
Yeah,
Okay.
all October.
Oh, I'm sorry. I should have said. I'm sorry. I should have said. You're right. I should have said
Okay.
October. Sorry, my fault. I should have said October 1.
That changed my answer.
Nice mistake to have.
Yeah, that was a convenient error.
Okay. Alright, so now, So it's so every time you split it in half, and 2 to the 10th is 1024.
But now don't you have to guess between October and November?
Even once you get down to the month, you've still got a
November and
30 or
December.
31 days to get it.
So November 15th, you go in the middle.
Right, you go in the middle. And every time I have how much of the year is left. So initially I have 365 days, 366 days to play with.
And over.
So you
Right.
keep splitting. It's
So you
the
keep
same way
splitting.
if you do pick a number 1 to 100, you do the same thing.
Exactly.
Yeah.
So basically this is binary search. And so, binary search is extremely efficient. And so the number of steps it takes is essentially the logarithm of the sample size. So I have 1,000 possibilities. It's taking me the log of 1,000 base 2 steps to get your birthday.
But you don't have 1,000 possibilities, you have 365.
I know, so it's even better. So
Okay.
I could probably do it with 9 steps. And
Oh, you're saying because you were doing 10 steps and kept cutting them in half. Is that
exactly.
okay?
I'll be safe, and I can make a few small errors as
So,
I did here.
but being that you're looking for a birthday,
Right.
what's the minimum number of guesses, I guess, that you could do? Because you're saying 10 guesses, but that's way too many.
Maximum.
So what would the
Well, worst case,
maximum? Yeah,
worst case, I think I could need as many as 8.
8. Because 9 would be 512, right?
Right.
But 8 is 256, that's not enough.
Right. So I guess
So the max would be 9.
So maybe 9. So that would be 512.
And you would definitely get it within 9 guesses. Cause,
Yeah.
okay.
So I guess I would need 9 guesses to be sure.
So you could actually that with kids do it.
Exactly.
They know, because a lot of people know that if you're guessing a number, like, they wouldn't know how I came up with the number 9.
Right.
But they know, I would think at 14 years old, that by guessing a number, you keep going in the middle of what you're
Right.
saying. But they don't, it doesn't mean that they know how many
Right.
guesses it would take.
I mean, how many of you have seen something like this before? This is one of the most important methods in mathematics. So I'll give you one application of this. This is solving equations, finding roots. So imagine I have a function which is continuous. And I want to find out where the function vanishes. And so let's say I know the function is negative here and positive at the endpoint over here. Well, if my function is continuous, I can't go from a negative value to a positive value unless I go through 0. So my function has to vanish somewhere in between. So if I want to numerically find a root to my function, I now split my interval in half, and I check and I say, oh, it's positive over here.
Vanishes means equals 0?
Equals 0. So there has to be a root of my function now between 0 and 1/2. So I split my interval in half again. My function is negative here. And so again, when I'm doing something like this, I don't have to be able to evaluate my function exactly. I just have to figure out, is it positive or negative? So now I split it in half again. And it's positive over here, so I know the root is somewhere between here. And now, so we're going to draw here approximately where the 0 is going to be, in fact. And so this is a wonderful method to find solutions, to solve f of x equals 0. So it's divide and conquer.
What if it had more than 1 0?
So if it has more than 1 0, then the question is which 0 will it converge to?
Because if it had
Yes.
a second time between your first 2 guesses.
Right, so if I had something like this, I would miss those 2 zeros.
But you don't know if you're finding the first or the second or the
Absolutely,
third.
correct.
But
And so,
rather than algebra, you just use calculus to find the zeros. No?
how would you use calculus? I mean, you're talking like Newton's method?
Well, if you have a continuous function.
Right. But how do you solve it? So I mean, let's say I give you, x, e to the x minus 5 equals 0. We don't know how to solve transcendental equations like this. We know how to solve polynomial equations. Even once the polynomial gets to degree 5 and higher, that's tough. But x to the 5th minus 5 equals 0. That's an extremely hard equation to solve. We can approximate a solution to it. And we can use this method of divide and conquer. It turns out using powerful techniques from complex analysis, sometimes you can even tell how many roots a function has in in a window. So if you only found this root, you would know, okay, let me try it again, but let me try it with a smaller step size. And then with a small step size, I might find something like this. One of the real dangers in a method like this is if the function looked like this. And what if it had 2 zeros exactly at the x-axis? Very hard to find something like this.
Double root.
Double roots are very bad. And so there's lots of different techniques to handle stuff like this.
You would just not only would you underestimate the number of roots, you'd also start getting the signage wrong on the other side, right? Or you would just miss it. I guess you just miss it entirely.
You would just miss it entirely.
Yeah.
And so even if you knew how many zeros there were, if there's a double root, it's going to be a real pain to find. What you would have to do is you would have to start looking at small windows and see that the function gets really small.
Yeah.
But, how do you tell the difference between it actually hits the x-axis or it's just a little bit above the x-axis? If people are interested, there's generalizations of this using calculus, which leads to fractal geometry and those different chaos patterns. And so, if people want, that's definitely something we can talk about after lunch. But what I like is all these things are connected. And so when you start talking about why do we care about different bases, well, there's lots of applications. It's computer storage. It's binary search. It's transmitting information. There's a reason why we've developed all these tools and techniques. And they can be used for a variety of things in addition to just solving MCAS and other problems like this that you just grilled on. These have real-world applications. If you think about how many people do online shopping, you need to have secure information. You need to be able to transmit securely. So if people want after lunch, I'm happy to go through, it's a fun example using pirates. How can 2 people agree upon a secret yelling in a crowded room? So this is the worst possible case for transmitting information. Is the eavesdropper is right there and hears everything you say. If you want to buy something from Amazon or eBay or Target or whatever, you don't go down to their company headquarters and say, "Hi, I'm Steve. I'd like to buy some stuff from you in the future. I'd like to agree upon some security words with you and some passwords and some systems right now." You're not going to do that to all the different online sites. You go to this online site. It's kind of amazing this faith you guys have. And you go to this site that you've never been to before, but some of your friends have gone and they've had good experiences. And you give them all your personal information. And you hope that only the store gets that information. And they will then contact your bank, and they will take the money from your credit card.
So for instance, when I sign on my school email,
right,
a message comes up exchanging
protocols.